All right. We'll look at reviewing here our Chapter 9 work here where we're solving systems of equations. I'm looking at two variable systems with linear equations. And you can see here in these first three examples, wants us to solve algebraically using the substitution or the elimination method. So again, our goal in solving the system, if it's consistent, is to find the ordered pairs, x, y, that satisfy both equations, which means graphically where they would intersect. So do they have a solution? It's possible, and they could have one or infinite, or they could be two parallel lines that would never intersect, what we call an inconsistent system. There'd be no solution, no intersection point. So we have three scenarios we run into when solving a system of equations here with two variables. Now let's go and look at the example here. Now with the substitution method, so I'll show you substitution just to show you can pick whatever method you like. Now the substitution method, and again, remember your goal in solving algebraically, whether using substitution or elimination, is to get down to one variable. So with substitution, you do that by picking an equation and picking a variable and solving for it. So let's do that. So I'm going to solve using substitution. And my first step is I'm going to solve equation 1. I'll call the top equation, equation 1. And the easiest thing to solve for would be x. Now you can pick either variable, x or y. But let's solve that for x. So if we do that, right, we would need to move the 7y over. So x would equal 7y minus 21 as we add that 7y over to the right side. And then we get an expression that we can substitute. So we take that and we substitute into the other equation. So this is your substitution step. So you're ready to substitute. So that implies 3 times x. Well, x is equal to 7y minus 21 minus 6y equal to negative 18. So out went x, and then what? It equals. So again, I'm taking out that variable. Well, now we've got an equation, a linear equation, with one variable, that variable being y. So we'll be able to find half of our solution doing that. So as we distribute, 3 times 7y, that's 21y. 3 times negative 21, that's negative 63, minus 6y equal to negative 18. And as we're simplifying and solving for y, we need to combine the y terms. 21y minus 6y is 15y. All right, so while we're at it, let's go ahead and add. We'll move the 63 over. So we'll move the constant over to the other side of the equation. And as we do that, we get 15y equal to 45. Right, negative 18 plus 63. And then we would divide out our coefficient. So as we divide out 15 on both sides of the equation, we get y equal to 3. So there's half of our answer. So y equals 3. So now we got to find x. Right? And to find x, we're going to back substitute. So we're going to go back up to the beginning. Now you can always plug into either of the original equations, but the easiest thing to do is to go back up and plug into step 1. So again, remember, if y equals 3, that implies x equals 7 times 3 minus 21, which is equal to 21 minus 21, which is equal to 0. So there's our value of y, or x, I should say. So we come up with x equals 0 when y equals 3. So what's our solution? So as we write out our solution, this is a solution, again, with an ordered pair of 0, 3. Which means our system is consistent. So it could ask you what kind of system are you dealing with. And remember, consistent means it has a solution, whether it be 1 or infinite. And with that said, we also have independent equations. So these equations are independent of each other. All right, so again, that's the substitution method. So again, going back up and substitute. Now, with that said, right, what do we want to do? Let me go ahead and move on here. Our next one, we want to go on to, now you can check. We should take our check step, right? You should always check it, either plug them back into both original equations. For example, if you plug in the bottom equation, 3 times x, 3 times 0, minus 6 times y, is minus 6 times 3. Well, that's 0 minus 18, that is negative 18. Same thing in the top equation, right? 0 minus 7 times y, 7 times 3 is 0 minus 21, which is negative 21. Or you can graph them. You graph them, you'll see your intersection point at the ordered pair 0, 3. So it's a consistent system, independent equations. Now I'm going to turn around and look at number 2 just to show you a different method. And number 2, I'm going to use the elimination method. So let's do this one with elimination, just to show you each type. Again, you pick. So I've done one with substitution. Let's do one with elimination method. Now, elimination method says to eliminate a variable by addition. So when I'm looking at this system, the first thing I'm going to do is go ahead and rewrite them in standard form. So let's go ahead and get these equations in standard form. So we got 3x plus 3y. Let's get the variable terms on one side and the constant term on the right. So here we got 6x plus 6y equal to 49. And right now, right, if we were to add these two equations together, right, nothing would eliminate. We get a 9x plus a 9y, and we get what? 100? Well, that didn't help me. We got to eliminate a variable. So we got to make the coefficients of x or y be opposites. That's our work with the elimination method. So make these coefficients opposite of each other. You choose your variable. Well, as you look at the coefficients on both of these, it wouldn't matter. You're going to see that both have the same coefficients, which probably tells you about what type of outcome you're going to get already. But just say we were focusing on the x term. So right now, what I'm going to do is I'm going to rewrite both of these equations with the opposite coefficients. So what I'm going to do is identify the least common multiple of 3 and 6, which is 6, right? 3 times 2 is 6, 6 times 1 is 6. So let's go ahead and reintroduce both of them with a 6. So we can do 2 times equation 1. Well, 2 times equation 1, that's what? Multiplying everything by 2. So that gives me a 6x plus a 6y and 102. And then to get a opposite, we need a negative 6x. So to do that, I'm going to multiply equation 2 by negative 1. Right? Because we want to make it the opposite. So we got negative 1 times negative 1. Got to do the same thing everywhere to keep it equal. So that'll give me a negative 6x, a negative 6y, and a negative 49. And now we can add them up. So when we add these up, what do we get? Well, we eliminate the x term like we wanted, but of course we've also eliminated the y terms. So we get 0. So 0 equal to, well, what's 102 minus 49? That's 53. Right? Well, 0 does not equal 53. So we get a false statement. So we aren't able to solve, right, for x or y. And we get a false statement, which means we have no solution. It means these two lines are parallel. So that's another conclusion. If you want to check it graphically, these are lines with the same slope and different y-intercepts. And this is an example of an inconsistent system. This one's inconsistent. All right, and independent equations. So again, that's looking at no solution. All right, so we've seen two different scenarios come into play. All right, we've seen one solution, which we did with substitution method. We've seen an example here with no solution, right, using the elimination method. And let's go to this third example. And let's do this one here, and I'm going to do it. I like the elimination method, so I'm going to do it the exact same way. Let's do it with the elimination method. So using the elimination method again, And we'll focus in on x or y. Now let's say we want to do the y terms, right? So we want to get rid of y. So if I do elimination method, let's write the equations here beside it. So again, elimination, we're looking at this system. Right down here beneath it, 2x minus y equal -1, and -4x plus 2y equal 2. Nice thing about this system is already in standard form. All the terms are already lined up nicely. But if not, we want to rearrange them, line them up. But yeah, eliminating y, right, we need to multiply equation 1 by 2. Right? We know that 2 times -y will give me the opposite -2y term we're looking for. So let's go ahead and do that. So as we time both sides of the equation by 2, we get 4x minus 2y equal to -2. And our second equation, which I hadn't done anything to, is -4x plus 2y equal to 2. Well, as we add these up, again, we eliminate our variable. What happens? We get 0 equal to 0. So this time, we get a true statement. So a true statement results. So true statement results, that implies infinite solutions. There's not one order pair that works. There's infinite order pairs. Infinite solutions. This is a consistent system. I'll write that up here with dependent equations. All right. So you've seen each of the 3 scenarios that you could have. All right, you have one with one solution, example 1. You've got one with no solution. Again, a variable is eliminated, a false statement. And then we had one with infinite solutions, true statement results, right, from the variables being eliminated. And it means infinite solutions. Now, with that said, we should make a note. These solutions are restricted to ordered pairs from one of the 2 equations. So you could write it in set form. But you're good enough with just writing infinite solutions. That'll be fine on your test. All right, let's move on. Let's look at determining the order of a matrix. So now we're getting into our matrix operations. In determining the order of a matrix, you're counting up the rows and the columns. So remember, order is rows by column. So count up your rows, right? And then count up your columns. So we've got what? 1, 2, we've got 3 rows. And we've got 1 column. So this is a 3 by 1 order. So there's my order. 3 rows or 1 column. All right, moving on down. It says find the values of the following variables. Now, as you notice, we have an equation with 3 variables. We've got m, we've got x, we've got y. Now this is a matrix equation. So if 2 matrices are going to be equal, they've got to have the same order. So what's the order? I'm going to write it beneath. They have 2 rows with 3 columns in both of these matrices. These are both 2 by 3 matrices. So yeah, they have the same order, right? And then we got to have same entries to be equal. So let's go ahead and do that. So same order and the same entries. So that implies, so if we look, row 1, column 1 entries. Well, that implies we know that 4x would need to equal -8. And then we can solve that. So we solve that for x, right? We get x equal to -2. So there's one of my 3 unknowns. Now, as you go to your y term, right, let's look at the y term next. Got -3y and 3. Those are the row 1, column 2 entries. So that implies -3y must equal 3. So we divide out a -3 on both sides, y equal -1. There's 2/3 of our solution. And you'll notice, what's row 1, column 3 entries? Those are both -6. They equal. Same thing here. We got row 3 or row 2, column 1 entries are both 1. Now as we move on to, as we look at row 2, column 2, we get to our last variable. We got 2m. and over here we got an 8. So that implies 2m must equal 8, which as we solve for m, we get m equal to 4, right? So again, we've solved for those variables. So again, that's matrix operations. So let's get into matrices, and we'll continue on here on our next page doing some more operations of matrices, looking at addition, subtraction, scalar products, and multiplication. But we'll take a break and come back to those.